I want to show you how important steady state is for running this equation by showing you how ridiculous the numbers are you get as an output when you try doing this for a patient who is not at steady state and has had some acute change in their ventilation. So let's consider a patient that is hyperventilating initially, and then some acute change happens where they hypoventilate instead. So you might see this if a patient has a high amount of pain and that's causing them to hyperventilate, and then you give them a huge dose of opioids, or maybe a reasonable dose, but they're sensitive to the opioids. Now suddenly they're hypoventilating instead. So they've gone from a rest rate of 20 to, let's just say, for the extreme of this example, that they've gone apneic. This patient was on room air, so the O2 that's brought in is 150, as we've been using. Some currently unknown amount of oxygen has left the alveolus, gone on to our tissue, where it's being converted to CO2 at a ratio of approximately 1 to 0.8, and then being brought back and measured in our arterial circulation. So we'll have some PaCO2 here. Let's take an educated approach to inventing what this PaCO2 would be. I think up here we said that the resulting PaCO2 from breathing at a rest rate of 20 was going to be about 30 millimeters of mercury. So let's say it would have been 30 millimeters of mercury here, but the patient has been apneic for a whole minute now, so this is going to be higher. In the first minute of apnea, the often quoted increase of your PaCO2 will be about 12. So we'll say we add 12. Actually, let's just add 10 to keep our numbers simple. 10 millimeters of mercury. So we're going to say that this guy has 40 millimeters of mercury in his arterial circulation. And we got to this by saying that he was at a lower PaCO2 from hyperventilating for a long time and reaching a steady state here. But then now we've added 10 millimeters of mercury for the last minute of apnea. Of course, this equilibrates with our alveolar CO2. So we have 40 millimeters of mercury of CO2 in the alveolus. So we know we've made 40 of CO2. And to keep these proportions, that means that we must have metabolized 50 of oxygen. So we can say that the O2 out was 50 millimeters of mercury. 150 minus that 50, so the 150 we brought in minus 50 is 100. So for calculating our AA gradient, we at least have our alveolar tension now that is supposedly 100 from our alveolar gas equation. Now we just need to invent a reasonable PaO2 for this guy. So let's say that he has an FRC of 1,000 mils. We recently talked about how a normal FRC is about 2,000 for a 70 kilogram person. So maybe this person has obesity and OSA, and that's why they were so sensitive to the opioid dose that you gave them, and they're also supine, so their FRC is further decreased. They were on room air, so they're breathing 21%. So basically at the time that they went apneic, they only have 210 mils of O2 in their lungs. We've also talked about O2 consumption and said that was about 250 mils per minute. So after a minute of being apneic, we've essentially burned through 250 mils of O2. So we've actually used more oxygen than is even available in this patient's lungs. So if we were to measure our resulting PaO2 in this patient, he's definitely going to be a little bit hypoxemic because he has no more oxygen left in his lungs and we're just burning through the oxygen that's bound to his hemoglobin. So maybe his oxygen tension is 40 millimeters of mercury, and that's corresponding to a SAT of about 75%. So back to our AA gradient, 100 millimeters of mercury of oxygen in the alveolus, supposedly minus 40 in the arterial circulation, gives us a gap of 60 millimeters of mercury of oxygen, which really doesn't make any sense for this patient. This is a high gradient, very high. But all we've done to this patient is lowered his ventilation, and low ventilation is supposed to be a normal AA gradient hypoxemia. So this is incorrect. While the alveolar gas equation would suggest to you that since this is a high gradient, maybe this person has a shunt now or diffusion abnormalities, but literally the only thing we've changed here is the ventilation of the patient. The low minute ventilation is supposed to be normal gradient. The alveolar gas equation here is not valid because ventilation was changed without establishing a new steady state PaCO2. And actually, if you're apneic, the steady state of your PaCO2 doesn't even exist because it would just keep going up and up and up. The problem is the resulting increase in your PaCO2 lags behind any clinically significant increase in your O2 consumption. So until you have a PaCO2 that is unchanging with your new ventilation settings, the alveolar gas equation will not be accurate. And it will do things like trying to tell you that this patient has a high AA gradient even though you know that they don't, and that their alveolar O2 concentration is actually much lower than 100 here. Okay, I think I've said enough about that. Now we'll finish up with talking about something much easier.